Now the next improvement that we can make to the carry skip adder is basically what's called a carry look ahead adder. So if you remember in the carry skip adder, if we had a group of 4 bits, we were still having to propagate the carry through 3 of the 4 bits in order to figure out what our generate value looks like based on just those 4 bits alone. So we kind of had 3 bits worth of that AOR function that we needed to do for each group of 4 bits. As opposed to doing that, what we can try doing is looking at those 4 bits and calculating what the carry out of those 4 bits is, all in a single stage. So trying to use a higher fan-in cell that looks at A sub 4 through 1 and B sub 4 through 1 all in combination instead of propagating through. And then that allows us to, in the very first set of stages, get a faster delay. And if you remember, the first set of stages we had to propagate through 3, and the last set of stages we had to propagate through 3 when we were breaking it up into 4 bits. What if you only had to go through 1 at the first stage and 1 at the last stage, just using a different combination of logic for that group of 4 cells? So that's kind of what a carry look ahead adder is. It's trying to use higher valency or higher fan-in cells that use more than just the 2 inputs of A sub 1 and B sub 1 at each individual bit. Now let's look at the delay diagram that we could get for a carry look ahead adder that we were talking about using in the previous foil. So in this case, using carry look ahead, we'll design stages instead of propagating through a carry propagating through 4 stages. We'll design a really complex single stage to do the same function in a single stage instead of waiting for 4 stages worth of logic. So that these single stages of carry look ahead are being denoted by the circles as opposed to the squares. And so you can see the longest path through this particular design is if we take bits 1 through 4 and do a combined carry look ahead function on that. At bit 4 you can see the black circle for that combined carry look ahead function. Then we have our kind of normal carry skip at bit 4, which is the gray square. Then we'll go through that carry skip at bit 4, skip to the left to bit 8, and we do a normal carry skip again at bit 8, skip to the left and bit 12. So we've gone through 3 of these normal carry skips, and now at bit 12 we have a normal kind of carry skip at bit 16, but then we have the 3 carry look ahead complex functions at bits 13, 14, and 15. Now the slowest and most complicated one of those is going to be at bit 15 because you have the most inputs. And the more inputs, generally a single stage is going to be slower if it has more inputs. So our slowest path is going to be through bit 15 there. And so you can see the total amount of time delay through this particular carry look ahead design would be the black carry look ahead complex logic at bit 4 plus a similar type of logic at bit 15 at the end. So those are going to be generally longer delay stages because they have lots of inputs, plus 3 normal carry skips in the middle, the gray squares. So the total delay would be about 5 stages, 2 of which are going to be complex logic and slower, and 3 of which are going to be faster normal carry skips. But in general, it'll probably be a little bit faster than our previous carry skip, but it's hard to tell for sure in this particular design because it depends on how much slower those circular complex stages are going to be. So it's worth evaluating the difference there, but this can definitely give you a faster design if you design it carefully. I mentioned on the previous foil that these carry look-ahead functions can be slower. Here's just a look at just an example of the previous foil where we had 4 bits that we were combining together. This is a depiction of what type of gate we would have to create for a generate of 4 bits. So basically we're doing an and or function for the total number of inputs that we have, and we could basically, you could plot this out in terms of transistors, what you would need in order to make this, but you'll definitely find that this type of structure with the number of series and parallel devices will add more capacitance, series devices will add more resistance that you need for your drive strength, and so this gate is definitely going to be a lot slower than you would get from just a single 2-input XOR or AND/OR function. So just be careful with how big you try to make a given stage, because at a certain point you might find that that stage is so slow that it's better to do 2 stages with less inputs. So another trick that's sometimes used is what is called a carry select adder. And this is a trick that you can use for not just adders, but you can use it for other functions that you might want to use as well, where you know that you have maybe 2 inputs that are fairly stable and they're there early, and you have 1 input that might come in later that's late. So what you can do is you can pre-compute the answer as if the input that's late was both a 1 and a 0. So you compute both results and have them sitting there waiting, and then you just select which result it is once the late input comes in later. And so this saves you at least the very end delay time for the last bit. So as your carry is propagating through, you can see in the diagram below, we have basically for each group of 4, we're calculating 2 separate sums. We're calculating one sum on the top adder of each group of 4 that is assuming the carry in is a 0, and we're calculating a different sum on the bottom shown row of sum signs as if the carry in was a 1. And then we have those going to a mux at the end, that when the carry finally does arrive, we just select the sum based on that carry at the very end. Now this saves us, it isn't necessarily all that useful for bits, let's say 8 through 5 and 9 through 12, because those weren't our critical path for the sum anyway. But you might want to use it for your higher order bits, because the sum 16 through 13 would have required the value of carry sub 12 to come in and then ripple through 4 bits in order to get the final sum sub 16. So it could be most useful for your very high order bits, might not be quite as useful for the lower order bits. And the thing to keep in mind is this definitely can save you delay, but it's going to take up a lot more area and it's going to use more power because you have to calculate twice as many sums in order to get your final answer. And so the area and power might not be worth the delay benefit that you get depending on your application. The carry select that we talked about in the previous slide was saying, if you remember, we're calculating for each bit, we're calculating 2 sums. Sum as if carry in was coming in as a 0 and carry in coming in as a 1, and then we were doing an XOR. So a different way that you could do that is there's, for those 2 sums that you're calculating, there's actually some P and G logic that is in common that could be shared between those two sums. You don't need to do two full adder sums per bit. You can do the PG logic the same for each bit, and then you could have the final sum value separately for each carry in 1 and carry in 0. So this splitting out the logic in that way is what's called a carry increment ladder. So you share the PG generation for each bit, and then you have that mux function incorporates the logic for carry in 0 versus carry in 1. And here we can see the delay graph if we did that. So the PG logic is shown in black, and the donation or denotation of the carry in coming in and performing its function is in gray. So this is showing what we could get for the delay through the full adder if we did that functionality for a carry increment adder. So here you can see we have, if we start in the upper left as normal, we ripple through the first three bits, and then we have a value from bit 3 that's used in common for bits 4 through 7. So we go through the first 3, we skip over to bit 7, we go down and we skip over to bit 11, and then the final delay is going to be bits 12 through 15 all get calculated at the same time. So in effect, we now have 6 delay elements in this design, as opposed to, if you remember from previous designs, the best previous design we had was 7 delays. So this carry increment adder can now bring that down to even 6 for a 15-bit adder. And the actual function for this is we have our time to propagate through the P and G, propagate and generate values at the beginning, and then we have a T XOR at the end for the last bit calculating the sum, and then the delay through the middle bits is n-1 plus k-1. So instead of that n-1 times 2, in this case it's just n-1 by itself plus k-1. So for a 16-bit adder, that's 4 minus 1 is 3, plus another 3, we have a 6. So you can see we've greatly improved the delay from the simple ripple adder, which was 16. We're almost about 3 times faster at this point. But wait, we can do even better if we take the carry increment adder that we just talked about and now did a variable group size with that design. You can see in this, in the upper right, you can see where we have now, if we have the group sizes a little bit smaller on the right hand side as we're initially defining our carries, and have it a little bit larger on the left side, you can reduce our delay by 1 additional delay stage. So you can see here we only have 2 bits at the beginning, and then we go to bit 3. So we start off, go through a carry generation at bit 1, and then we have 2 bits grouped together, so we jump to bit 3, and then we jump to bit 6, have 3 bits together, and then we lump 4 bits together, and we jump to number 10, and then we lump 5 bits together and jump to 15. And so in this case, you can see there's 1, 2, 3, 4, 5 delay stages instead of the 6 that we had previously. And then what's shown in the bottom figure is something that doesn't reduce our number of delay stages, but it's something that can reduce our total delay. So note that the output from bit 3, so if you look up in the diagram on the top, the output from bit 3 needs to go to 3 receivers, bits 4, 5, and 6. So it has a fan out of 3. That's going to slow down the output from bit 3 because it has more capacitance to drive. So what we can do is we can add a buffer at the output of bit 3 that drives, the output of the buffer drives bits 4 and 5, and the output before the buffer drives solely to bit 6, because our critical path is to the higher order bits. So if we can drive to bit 6 with less capacitance, so driving a buffer plus bit 6 is less capacitance than driving bits 4, 5, and 6 together. So we can speed up that path to bit 6. Then we can do a similar thing from bit 6 to bit 10. We add a buffer in there that drives bits 7, 8, and 9, and so we get a faster delay from bit 6 to 10. Unfortunately, we can't play that trick on the last stage because bits 11, 12, 13, 14, and 15 are all happening in parallel at the same time. So no one of them is necessarily slower or the most critical one. They're probably all critical at that point. So the last stage that has the most capacitance, we can't really do anything about because we need all 5 stages to receive the carry coming in at the same time. So we've been doing this carry skip and carry look ahead, and as I've mentioned before, when we get to really large adders, like we're getting up to 64-bit or 128-bit, obviously the carry path is the dominant path through the adder. And so, we've been saying, well, we've been doing this look ahead. Look ahead is good. So how about we try using a look ahead across the look aheads? So if we do something like that, something basically a recursive look ahead, we instead of getting a square root of n, we can get kind of a log of n delay through an adder. So next we'll be talking about tree adders where we do look ahead across look ahead. And there's many different variations on tree adders. We'll be going through some. We won't be talking about them in intricate detail. There could be many hours, if not days, of study on all the different types of tree adders that are out there. But we'll at least talk about at the high level some of the different designs that are out there and what the benefits and why you would use different designs by name. We'll present the names of various different designs and why you might want to look at different designs over others, the trade-offs, and which ones are better at what types of parameters that you're trying to design to. So the Brent-Kung adder is an adder that goes by a log scale. So it first calculates prefixes for a 2-bit group, and then it uses the resulting output from that to calculate prefixes for a 4-bit group, uses the result from that to calculate prefixes for an 8-bit group, and so forth. So you can see one example here for a 16-bit adder. If you look at the highest order bit, 15 there, you can see it takes one input for the first 2-bit group from 15 and 14, and then it takes for the next group, it takes the 13:12 group combined with its 15-14 group and gets 15 through 12. Then it takes the 15 through 12 combined with the 11 through 8 group and gets 15 through 8, and then combines that with the 15 through 8 group with the 7 through 0 group, and you can see we've gone through 4 of those stages for 16 total bits, but that particular group isn't the slowest. The slowest you can see actually is more bit 14, where you had to go through various different stages, and I'll let you look at how that propagates through and you can see that the slowest bit in this particular case is bit 14. So each one of these adders we'll be talking about. I'm not going to go through the details of what each stage and each calculation looks like. If you want more details, you can basically do a search for Brent-Kung adders and get into the intricate details. But this is just showing you functionally how this adder would get the number of stages that it has. So a different adder tree is the Sklansky adder tree, and this one has a benefit of it's basically computing the large group PG functions along with the small group at the same time. So you can see there's actually less number of stages through this. The trade-off that's being made here is if we go back and look at the previous Brent-Kung adder design, you'll see that each driving stage of a given PG output only drives at most 2 receivers. Whereas in order to calculate the large stage and the small stage combos at the same time, you can see with each stage you go down, the next stage will have basically double the number of things that it needs to drive. So when you're looking at, like, let's say the black 3:2 stage, out of bit 3, it's only driving a single receiver. When you get to stage 5 though, stage 5 is driving 3 things, and stage 9 is driving 3 things. When you go down for stage 11 for 11:8, after you go down 2 stages of the black squares from bit 11, that second black square is now driving 11:8. It's basically having to drive 5 different receivers. And then if you go down to the third stage, looking from bit 7, starting at the top of bit 7, you have a black square and a second black square, and then the gray square. That gray square is now driving basically 8 bits plus the buffer. So it's basically driving 9 bits worth of data. So you can see it's pretty heavily loaded the way this design is. So you can see less number of total stages of delay, but the larger your adder is, the more stages you have to drive for the higher order bits, and so it can slow down the critical path by quite a bit just based on large amount of fan out. So that could be problematic depending on all the other trade-offs you're making in your design. So the Kogue-Stone design or adder tree is using a similar way of trying to calculate the large tree combinations and small tree combinations at the same time that we just talked about on the previous foil, as well as only doing a fan out of 2 for each stage that we had talked about 2 foils ago with Brent-Kung. So this adder design gives us a similar log function in terms of delay. So we have a 16-bit adder that, since it's based on a log base 2, only has 4 stage delays through it. But the trade-off here is you can see just how many wires there are that have to be wired between each stage. And so this can be problematic for the area in layout trying to wire this up. So if you can make do with the area that this would require, or the number of wires that this would require to try and wire it up, especially for a really large adder for 16-bit, this looks kind of bad. If you were doing a 64-bit, it might look like a nightmare. And so you're trading off, again, wire area for amount of capacitance, driving capacitance that you need to drive versus delay. And so there's various different trade-offs that you can make with each of these adder designs. On the previous three foils, we talked about three different tree adders that each had their own trade-offs in the design. And we'll go through a little bit more on that right here. So it turns out that there's a taxonomy that exists to describe tree adders. So first let's go through what an ideal n-bit tree adder would be. So n is the number of bits in the adder. So the first thing is the number of logic levels. So the best that we've been able to do so far is based on n number of bits, the least number of logic levels that we've needed so far is a log base 2 of that n number of bits. So the best n-bit tree adder minimum number of logic levels would be log base 2 of n, where n is the number of bits. Next, looking at the fan out for any of the tree adders we've looked at, the best fan out that we've had as far as the smallest fan out for any given stage is a fan out not exceeding 2. So 2 is the best fan out that we've been able to do. And then the number of wiring tracks, since we did discuss that, we would want no more than one wiring track between levels. So the best, this is the ideal adder. Turns out you can't get all of those at the same time in the same adder. So we found that we can describe an adder with a 3D taxonomy based on three variables: a small case L, F, and T. The small case L is it's used to determine your total logic levels. So the total number of logic levels will be the capital L is the lowest number of logical levels we can get, plus small case L. The total fan out or worst case fan out that we'll get is 2 to the small case f plus 1, and the worst case wiring tracks is 2 to the power of t. Now, what does the small case L, F, and T mean? So tree adders, it turns out, sit on a plane defined by the fact that L plus F plus T has to equal exactly the capital L, which is the log base 2 of the number of logic levels, minus 1. So just as an example, if we're using a 16-bit adder, that means capital L would be log base 2 of 16, which is 4, and 4 minus 1 is 3. So we can find a 3D adder tree taxonomy where L plus F plus T has to equal 3. So I'll go into that a little bit more in the next foil. As I mentioned, tree adders have a 3D taxonomy based on three parameters: L for logic levels, T for wire tracks, and F for fan out. So if we had here a 16-bit adder that I've been talking about on and off through the last few foils, like I mentioned, the L plus F plus T has to equal 3. So we could either have L equals 3 and F and T are both 0, or F equals 3 and L and T are both 0, or T equals 3 and F and L are both 0 for a 16-bit adder. And if you had here in this graph, you can see what values for logic levels you would get with L being 1, 2, or 3, what values you would get for wire tracks 1, 2, and 3 for T, and what value you would get for fan out with a value of 0, 1, 2, or 3 for F. So if we decided we wanted to choose, here you can see if we decided that we wanted to choose L equals 3, you can see in the upper right quadrant, that's actually the Brent-Kung design. So L equals 3, F and T are each equal to 0. So the number of logic levels for Brent-Kung design is 7, which is the base capital L of 4 plus small l of 3. So 4 plus 3 is 7. That's the total number of logic levels. And since F is 0, its value would be, the total fan out would be the 2 to the F plus 1. So 2 to the 0 is 1 plus 1. So you get a value of 2. And the total number of wire tracks would be 2 to the T. So 2 to the 0 is 1. So you get 1 wire track. A fan out of 2 is the largest, but you get 7 logic levels. Now, the other two designs that we previously looked at, the Cog-Stone is basically as if you had logic levels small l of 0, small f of 0, but T of 3. So here you see for a 16-bit adder, you see you'll need 8 wire tracks, but you'll only need a fan out of 2 and logic levels of 4. And then the Sklansky model is as if you were maxing out the fan out, but keeping the logic levels and wire tracks at the lowest value. So small f is 3, and small l and small t are 0. So that requires a fan out of 9. When you calculate 2 to the third is 8 plus 1, gives you a fan out of 9, but your logic levels is 4 because it has L equal 0, and your wire tracks is 1 because T is 0. So this gives you a way to kind of map out what the trade-offs are between those 3 different adder styles, where you're trading off fan out versus logic levels versus wire tracks. So another adder tree taxonomy is the Han-Carlson design. So the previous 3 designs we were kind of maxing out one of the 3 parameters that we were looking at, F, L, or T. This design is trying to balance between the logic levels and the wire tracks. So you can see this doesn't have the total minimum number of logic levels, but it does have less logic levels than the maximum amount for the tree adder. But it does have more wire tracks in it, but it doesn't have the maximum number of wire tracks that the previous design that we looked at had. So it's kind of balancing between the Cog-Stone and the Brent-Kung design in terms of logic levels versus wire tracks. The Knowles design, on the other hand, is doing a different type of balancing than the previous Han-Carlson was doing. It's also trying to balance between 2 of the parameters, but in this case, we're balancing between the fan out, the number of cells that any given output needs to drive, versus the number of wire tracks. So again, it's not maximum number of wire tracks that we saw in the Cog-Stone design. It's less than that, but it doesn't have the maximum fan out that the Cog-Stone design had as well. So it's balancing between those 2. So in this case, we're kind of balancing between the Sklansky design and the Cog-Stone design, where we might have a little bit more in terms of wire tracks versus fan out, but we have the minimum amount of logic levels. So we're not balancing off logic levels, we're balancing off fan out versus wire tracks. And last but not least, in our tree adder designs, we're looking at the Ladner-Fisher design, which here it's balancing again between two of the different parameters. But in this case, we're balancing off logic levels versus fan out. So the total number of drivers that, or the total number of receivers that a given driver has to drive. But you can see the number of wire tracks is minimized, and so we're not changing the minimum wire tracks, but we have a little bit more as far as logic levels. We have more logic levels than the minimum, but we don't have as much, but we have a little bit more fan out in order to balance between those. So in this case, we're balancing between the Sklansky design and the Brent-Kung design. Revisiting our taxonomy chart that we had seen previously, you can see that all of the different designs are shown here and how they are balancing between each other. So again, the Sklansky design is giving us maximum fan out and minimum logic levels, minimum wire tracks. The Brent-Kung design is maximizing, it has the maximum number of logic levels but minimizing wire tracks and fan out. And Kogue-Stone is the maximum number of wire tracks and minimizing fan out and logic levels. And then you can see the other adders are the points balancing between those three kind of outlier designs. And depending on what you're looking for, you can balance your adder to try and get some delay versus wire tracks versus fan out, and determine what works best for your particular application and choose the adder design that works best for you. And so once you choose what point you might want to look at, then you can go research that adder design in detail and figure out how to implement it in your situation. Here we have a good summary chart that basically is trying to summarize the various different adder architectures that we've just talked about with relationship to their area, power, and delay trade-offs. I'm not going to go through this in detail since we just went through it in detail. This might be a good thing you can use as a reference in the future. Just come back and either print this out or use this when you're if you need to design an adder and decide which design you want to use, or between the three tree adders listed there. Keep in mind there's the variations that are trying to between those three doing additional trade-offs. That's not included in this particular chart, but you can use this chart to help decide whether you want to use one of the alternate adders that might be doing additional trade-offs between the three main adders listed here as well. Okay, I know we've gone through lots of adder stuff and we're all sick of adders, but one last topic. That's what do you do if you have multiple input adders? So you want to add more than two numbers together. So far we've just talked about adding two numbers together. So suppose we want to add k number of n-bit words. In the example below, for example, we have 4-bit words, and we want to add 4 numbers together at 4 bits each. So one straightforward solution, we can take k minus 1 4-bit adders and just use a first adder to add the first 2 numbers together. The resulting output is added to the third number using a second adder, and then its resulting output is added to the fourth number using a third adder. So it would require k minus 1 total adders that are n bits wide. The problem is this is going to be large area-wise. We have 3 adders here now instead of just 1, and it's going to be very slow because it's 3 times the amount of delay as going through just a single adder. So let's go through how we can potentially solve this and make a slightly faster and smaller design. So one thing that we can note in making a multiple bit adder, or making an adder that adds more than 2 numbers, is if we go back to the full adder design for each bit that we had at the very beginning, we talked about how we have a value of A, a value of B, and a value of C in coming in. So we have 3 inputs to each bit of our full adder and 2 possible outputs, or 2 outputs come out. We have the sum value and we have the carry value. So let's, if we look at this in terms of an n bits, so let's say if we have a 4-bit using this carry and sum values coming out of 4 bits, we have 3 possible inputs. In terms of saying A, B, and carry, we'll say X, Y, and Z. So we have 4 bits worth of X, Y, and Z going in, and we have two outputs coming out, a C and an S coming out. So we get n sums and n carries. So it turns out that we can use that CSA type adder structure to take, instead of doing A input, B input, and a carry in, we can take 3 separate numerical values and send them through this CSA function and get n number of bits. So 4-bit output from that 4-bit CSA, we get 2 outputs. All of the C 4 through 1 and A and S, our carry and our sum, are both coming out of the CSA bits. Turns out we can, since our carries are in effect coming out as 4:1 and our sums are coming out as 3:0, the carry is actually shifted relative to the sum. But if we now send that into a 5-bit CSA, because the carry is shifted, so we need an additional bit, we can send those 2 values in along with our 4th data value as our bits 5 through, or bits 4 through 0, or 5 through 1, depending on how you want to do your bus notation. And then we'll get out of that 5-bit CSA, we'll get an additional C and S that are 5 bits worth. Again, the key shifted relative to the sum by 1 bit. And so then we can send that into a final sum stage, a normal adder, instead of these CSA functions, and add the carry and the sum together in a 6-bit adder and get a result out. And so final normal adder produces our sum coming out, which could conceivably be up to 6 bits, depending on the values of all of the different inputs. So this is a way to get a function of 4-input adder that produces a lot less delay than using 3 sequential adders. If you want more details on exactly how this works, the book describes it in a lot more detail. I'm just trying to give you the feel for what exactly is going on and what a CSA adder is.